Welcome back to Basic Electronics. In this lecture, we will look at a precision half-wave rectifier in which the op-amp does not enter the saturation region. We will then see how a precision full-wave rectifier circuit can be made up using the circuit blocks we have already seen. Finally, we will look at wave shaping using diodes and how to use it to convert a triangular input voltage to a sinusoidal output voltage. Okay, let us get started. Let us now look at an improved half-wave precision rectifier. And what is the improvement we are seeking over the superdiode circuit? The improvement we are looking for is that the op-amp should not enter saturation, because as we have seen, that affects the speed of the circuit. Let us see how this circuit works. There are two diodes now, D1 and D2. So we will take two cases, case 1 in which D1 conducts and case 2 in which D2 conducts. Alright, case 1, D1 is on. This loop is then complete and the op-amp operates in the linear region. Therefore, V minus and V plus are equal. V minus is 0 volts. What about VO1 in that case? VO1 is V minus this voltage drop, so that is 0 minus about 0.7, so VO1 is therefore minus 0.7 volts. Now if that happens, we can show that D2 cannot conduct, show that if it did, then KCL is not satisfied at this node. Let us do that. Suppose D2 did conduct. What would be this voltage? This is 0 volts, 0 minus 0.7 minus 0.7, so this VO would be minus 1.4 volts. This is 0, this is minus 1.4, so this R2 would conduct like that, and this R would also conduct a current going into that node, because this is 0 and this is minus 1.4 volts. So this current is going in, this current is also going in. So the only way KCL can be satisfied is for D2 to conduct in that direction. And that cannot happen because that would be the reverse direction for D2. So therefore, we conclude that D2 cannot conduct in this situation. If D2 does not conduct, then we have an open circuit here. And then R2 and R are in series. This end is at 0 volts, this end is also at 0 volts, so obviously we cannot have any current in this path. So this voltage drop as well as this voltage drop is then 0 and VO is equal to 0. So our situation now is D1 conducts, D2 does not conduct, IR2 is 0, IR is also 0. Let us now see what values of VI this situation corresponds to. So this is our current path, like that, and V minus is 0 volts, and the only way this can happen is if VI is positive. So the situation that we have discussed, D1 on, D2 off, can happen only if VI is positive. Clearly, if VI is negative, then we cannot have D1 conducting, and that brings us to the second situation, namely D1 is off. And let us look at this situation in more detail now. In this case, the conduction path is like this. Diode D2 conducts, and that is how the current flows. The loop around the op-amp does close, and therefore the op-amp operates in the linear region. V minus and V plus are equal. V minus is therefore 0, and because the current is flowing in that direction, VI is negative. So this is a consistent picture. Let us now figure out what VO should be in this case. That's easy to do. What is VO? It is equal to V minus plus this voltage drop. V minus is 0, and for this voltage drop we need that current. That current is the same as this current, and this current is 0 minus VI divided by R1, like that. And after putting it all together, we get VO equal to minus R2 by R1 times VI. So we have two situations: D1 conducting, VO equal to 0, and in that situation D2 does not conduct. D2 conducting, VO equal to minus R2 by R1 times VI, and in that situation D1 does not conduct. Here is the summary of the improved half-wave precision rectifier. Positive VI, D1 conducts, D2 does not conduct, VO is 0 as shown here. Negative VI, D2 conducts, D1 does not conduct, and VO is minus R2 by R1 times VI. So that's a straight line with a negative slope and going through the origin. And that is what the waveforms would look like. When VI is positive, the output voltage is 0. When VI is negative, the output voltage is positive. And in this example, we have taken R2 and R1 to be equal. So therefore, VO and VI are equal in magnitude. What is the big advantage of this circuit over the superdiode circuit? The op-amp always operates in the linear region. It does not enter saturation. And that is very clear if we plot this voltage VO1. And that looks like this. And clearly it does not go to plus minus Vsat. Let us see if we can work out what VO1 should be in each of these regimes. When Vi is positive, D1 conducts. This is virtual ground, so therefore VO1 would be minus V on. So that is what we observe over here. This is not quite minus 0.7. The exact value would really depend on the current levels. What about Vi negative? We have this situation now, and then VO1 is VO plus V on of D2, and that is what we observe over here. And in either case, the op-amp does not enter saturation since a feedback path is always available. Here is the circuit file for this simulation. Here is another improved half-wave precision rectifier. Looks very similar to the circuit we just discussed, except the diodes are now reversed, and as a result we obtain this VO versus VI relationship shown in this figure here. So take this as homework. Figure out the conduction paths when D1 is on and D1 is off, and obtain this VO versus VI relationship. The circuit file is also available. You can try out the simulation as well. We can use the circuits we have already looked at to make up a full wave precision rectifier. And here is the block diagram. Vi is the input voltage, VO is the output voltage, and the relationship between VO and VI that we would like is shown here. This is a half wave rectifier inverting. It gets Vi as the input. Its output is VO1, and the relationship between VO1 and VI is shown here. When Vi is negative, VO1 is 0, and when Vi is positive, VO1 is minus Vi. VO1 is multiplied by minus 2 to obtain VA, Now in this region, when Vi is negative, multiplying by -2 doesn't make a difference. So Va is also 0 here. In this region, when Vi is positive, VO1 is minus Vi, and multiplying that by -2 will give us plus 2 times Vi, and that is what is shown over here. Now this block here multiplies Vi by -1 to give Vb. So if we plot Vb as a function of Vi, we get a straight line passing through the origin with a slope of -1. And now what we do is add Vb and Va and obtain our final output voltage. Now when Vi is negative, Va is 0, so this part goes through as it is right there. When Vi is positive, we have a slope of -1 here and a slope of +2 here, so the net slope is +1, and that is how we obtain our desired Vo versus Vi relationship. Let us now see how this can be implemented with circuits. Here is a circuit implementation of the block diagram. This block is the inverting half-wave rectifier, and we have selected these two resistances to be equal so as to get a slope of -1 here. So this block gives us VO1 versus Vi given by this graph. So that is VO1. Now these other three functions, this multiplication by -2, multiplication by -1, and addition, these three functions are performed by this single block, the inverting summer that we have already seen earlier. What does it do? Let's look at the resistances. This is R, this is R, and this is R by 2. So VO is equal to minus Vi minus 2 times VO1, and that is exactly what we want. VO is minus Vi minus 2 times VO1 in the block diagram as well. So this circuit will perform full wave precision rectification. Here is a simulation result. That is our input voltage, the light blue curve, and that is the output voltage. And here is the circuit file. Let us now talk about wave shaping with diodes. What is the meaning of wave shaping? Let's say we have an input triangular wave and we want to convert that into an output sinusoidal wave. That is an example of wave shaping. Here is a simple diode circuit, and we will see that this can be used for wave shaping. We will take this node voltage as 0 volts, and there is a good reason for doing that, as we will see later. This node is sitting at minus V0, a constant voltage. It could be minus 5 volts or minus 10 volts, for example. That's the power supply. And what we want to do is to plot this V as a function of this current I here. First, let us consider D to be off, not conducting. So this is an open circuit. And when D is off, what is the current? It is simply V minus 0 divided by R0. So V by R0. And what is this node voltage with respect to ground? We have V here, we have minus V0 here, and this is an open circuit. So we can obtain VA by superposition, and that is given here. VA is V times R prime by R plus R prime minus V0 times R by R plus R prime. So that is our VA when the diode is not conducting. Let us look at this equation, and let us say V is positive. Now this term is positive if V is positive, and this term is negative as V increases, VA will also increase, and at some point it will reach 0.7 volts. Now VA becoming 0.7 volts means the diode turns on, and that provides a breakpoint in the V versus I relationship. So for D to turn on, VA should be V on, which is about 0.7 volts, and that gives us this breakpoint. So what do? We put VA equal to V on here and solve for V break. So V break then turns out to be R by R prime times V0 plus V on. This is a positive number, remember, because minus V0 is negative. That plus V on. So that is our V break. So when this voltage here is equal to V break, the diode starts conducting. And then we have this equivalent circuit. So the diode is now replaced with this battery here, let's say 0.7 volts. Let us now look at this current when the diode is conducting. It is composed of two parts, this current and that current. Now this first part is the same as before, V minus 0 divided by R0, that is V by R0. And this second current we can find by adding this current and this current. Alright, now when the diode is conducting, since this is 0 volts, this VA is equal to V on. What is this current then? It is V minus V on divided by R, that is the second term here. And what is this current? It is minus V0 minus V on divided by R prime, the third term here. Now we can combine terms containing V, that is V times 1 over R0 plus V times 1 over R, like that. And all the other terms are essentially constants because V on is a constant, V0 is a constant. So we can write our current as V times this 1 over R0 plus 1 over R plus some constant. In other words, if we want to write V in terms of I, that will look like this. This R0 parallel R comes from this term. And now we have all the information we need to plot V as a function of I. And that is the plot. So let us try to understand this plot. So when V is small in this range, the diode is off and the only current is the current through this R0, and therefore the slope of this part is R0. At this point, when V is V break, the diode turns on, and now the slope of V versus I is R0 parallel R, which is of course smaller than R0. So that gives us this segment here. So that is the overall V versus I relationship for this circuit. In summary, we have V break equal to R by R prime times V0 plus V on, that is the breakpoint there. And when the diode is conducting, V is given by R0 parallel R times I plus a constant. So if we look at this V versus I relationship, we notice that there are three design parameters. One, the slope of this part, which is given by R0. Second, the slope of this part, which is given by R0 parallel R. And third, this breakpoint, which is given by this expression here. And note that V break depends only on the ratio R by R prime and not on the actual values of R and R prime, whereas the slope R0 parallel R does depend on the actual resistance values. And therefore, given the breakpoint and the two slopes, the resistance values can be easily determined. And that is why this circuit is very attractive. All right. So what have we got so far? We have this V versus I relationship, and we have seen that this breakpoint is provided by this diode. When the diode starts conducting, we have the breakpoint. And this slope here is R0 parallel with R1B here. Now what we will do is to introduce another branch just like this first one with different resistance values, and that is what it looks like. What will this branch do? This will introduce one more breakpoint in the V versus I relationship, and we can design the resistance values such that this breakpoint, the second breakpoint, occurs after the first breakpoint. And what is this slope? This slope is R0 parallel with R1B parallel with R2B. We can now add a complementary branch like that. Note that the diode polarity is now different than this one. Also, this voltage here is positive, not negative. And with this branch, we can add a breakpoint in this part now of the V versus I relationship. And that is what it looks like. And you can work out the expression for the breakpoint in this case, and also what happens to the slope here and so on. And if we add one more branch like the first one, like that, then we have one more breakpoint like that. So this is the net V versus I relationship that we can obtain with this network. And now we will see how we can use this entire network for wave shaping. What we have done now is to place this entire diode network, which we saw in the last slide, in the feedback path of this circuit. Now notice that this circuit would otherwise be an inverting amplifier, and what we have done is to replace R2 of that inverting amplifier by this network here. And now it should be immediately clear why we took this voltage here as 0 volts. Because V minus and V plus are equal, this node is at virtual ground, and therefore it makes sense to treat that as 0 volts. And as we have seen before, the relationship between this voltage and the current is given by that curve. And what is this voltage in this circuit? It is the same as VO. So now we know the relationship between VO and I. Our next job is to relate this I to the input voltage VI. And that is easy to do because this I is the same as this current. And since this is at 0 volts, this VI is simply 0 minus this voltage drop, or minus RA times I. In other words, VI is simply a scaled version of I, and the scaling factor is given by minus RA. So using this fact, we can map this VO versus I relationship to the VO versus VI relationship, and that is what is shown over here. And of course it has got reflected around the y-axis because of this minus sign. Alright. So now if we apply an input voltage which is triangular in shape, that is what we get as the output voltage. And as we can see, it is close to a sinusoid. And in the next slide, we will see how good it is, how close it is to a sinusoid. Here is the SQL circuit file. You can run this simulation and check out these results. We will now look at the spectrum of VI as well as VO to figure out whether our output voltage is close to a sinusoid or not. Let's start with the input voltage first. Here is the spectrum. This is the fundamental frequency, let's say F. This is 2F, 3F, and so on. And for a pure sinusoid, we would expect this to be non-zero, but all others to be 0. And obviously this is not a sinusoid, and therefore we have non-zero components at these other frequencies. These even harmonics have got eliminated because of symmetry. So what is the measure of closeness to a sinusoid? We want these harmonics to be small. So in other words, this amplitude should be as small as possible as compared to this amplitude. This is our output voltage, and of course visually we can definitely say that it is closer to a sinusoid than the input triangular waveform. But we want to look at the spectrum now and say that more quantitatively. So here is the spectrum, and it should be clear when we compare these two figures that the relative magnitude of the third harmonic as compared to the fundamental has gone down for sure, and that indicates that our output voltage is closer to the sinusoid than the input voltage. To summarize, we have seen precision half wave and full wave rectifier circuits in which the op-amp works only in the linear region. Since the op-amp is not allowed to enter the saturation region, these circuits are relatively fast. We have also seen how diodes can be used for wave shaping, and in particular for converting a triangular input to a sinusoidal output. In the next class, we will simulate the triangle to sine converter circuit. So see you next time.